Settle down. Thanks for coming. This is a talk on Venice, a distributed database we've been building for the past many years at LinkedIn, and which we'll be open sourcing at the end of the talk. My name is Felix. I've been doing data infrastructure for 11 years, including the past 8 of which at LinkedIn. And Venice is a system that's been running in production for a while, more than 5 years. It powers 1,800 of our data sets, used by 300 unique applications. This talk is broken up in 4 sections. The first 2 are basically the user-facing aspects of Venice, how to write data into it, how to read data out of it. The third part is the operator's perspective, how do we operate Venice at scale. And then I'll close with a few words on the road ahead now that the project will be open source. Along the way, I hope that you pick up a few tidbits of distributed systems insights and hope you find it interesting. So writing to Venice seems to me like a natural place to start because whenever you consider using a new database, well, you got to write into it before you read anything out, right? So it doesn't really make sense to start from reading an empty database. But there is more. I think the way that we write into Venice is actually an important defining characteristic of the system. You see, Venice is a derived data store. It specializes in hosting data that's been processed out of other data. So think of the output of batch processing jobs, the output of stream processing jobs. More concretely, we have a bunch of Venice use cases that are in the AI space. So think, for example, of how you may want to retrain an AI model every day or maybe several times a day. And this AI training job could be outputting a large corpus of data, right? So we'll be reloading that data into Venice every day so that online applications can query that data at low latency. There are also some non-AI use cases that leverage Venice at LinkedIn, essentially building a materialized view of data that comes from elsewhere, right? The main thing to keep in mind with writing data to Venice is that all ingestion into Venice is always asynchronous. We think that actually improves the ergonomics of ingesting data from batch and stream processing jobs, as I'll try to make the case in the first section. And it is also a design choice that helps us carry out very high throughput ingestion, as I will also talk about. So the most popular way at LinkedIn to put data into Venice is using what we call the push job. The push job is essentially taking data from a Hadoop grid and pushing it into Venice. We have 2 flavors, the full push and the incremental push. The full push is working in the following way. So I've got like several diagrams that kind of look like this, so I'll just walk you through what that means, right? On the right-hand side, you've got the client that is reading data out of Venice. And in this scenario here, I'm showing that it is reading out of the current version of the data set, which is V1. This is an important concept right there. In Venice, data sets are versioned, and the version keeps kind of rolling forward over time, right? Now, when a full push comes in, Venice will dynamically instantiate a new version of the data set and let data be loaded in there in the background. What that means is, while data is loading, we don't want to affect online traffic, right? We don't want them to see a blip or incomplete data or anything like that, right? So when the full push is determined to have completed successfully and with full integrity checks, at that point, Venice orchestrates a swap of the read traffic onto the new version of the data set, which now becomes the current. And the older version of the data set becomes a backup that we retain for some period of time in case the user may want to roll back to it. So it doesn't really make sense to do more than 1 full push at a time, right? So because the full push is trying to swap everything, why would you swap concurrently? So that's treated as a user error if it happens, because typically it means people didn't configure their data flows properly and it's sort of accidental. Now, let us compare and contrast these characteristics of the full push job with the other mode it can run in, the incremental push. In this case, there is no swapping behavior. Instead, the data is incrementally added into the data set. And if you happen to have multiple versions of your data set, then it gets added to all versions of the data set. This is achieved by writing into a buffer, which is essentially a Kafka topic that is managed by the Venice infrastructure. And I'll get back in the next slides over why it matters to us to have this as a buffer. Another difference is that the incremental push does support concurrent writing. And our users like this because it allows them to take a bunch of different data sources that they may find in our grids and union all of these data sources together into Venice. Now, of course, they could run the union as a batch job in Hadoop and then do a full push of that. Some people choose to do it this way. But for a lot of our users, they find it convenient that Venice just offers that out of the box, and they can run like many very lightweight, independent incremental pushes. So far, we've looked at two techniques for writing data into Venice, the full dataset swap and the insertion of rows into the dataset, which are achieved by the full push job and the incremental push job, respectively. As we go through this section, I'll keep adding cells to this table to illustrate the range of possibilities that Venice supports. But before we go there, I also want to touch on some of our use cases want to do both of these things at the same time, right? They want to have full pushes and also incremental pushes. We call that hybrid. So hybrid workloads allow you to seamlessly combine batch and incremental writes into a data set. So I'm going to go through a quick scenario to show how it works, right? The beginning of the scenario is you've got the client reading V1 of the data set, which is the current version, and you've got a bunch of incremental pushes that are concurrently writing into that, right? Then a full push comes along, which, like before, dynamically creates a new version of the data set and loads that in the background without affecting online traffic. But then there's an extra phase to the orchestration. When the full push finishes, we do what we call a buffer replay. And you'll see why it starts making sense to have a buffer in there, right? So the look back period into the buffer is configurable. The user can choose to replay the last hour of recent writes, the last day, last week, last month. It's up to them, right? And what this means is that when you've got your full push data, which is, by the time it gets into Venice is maybe several hours old already because it's been processed for a while inside Hadoop, you don't necessarily want this sort of stale data set to go live directly. You want to refresh it up a little bit so you overlay on top of the full push your recent nearline writes, basically. And when we determine that we've caught up on the buffer replay, then the final phase happens just like before, that we swap the traffic over. So this is what we do in terms of ingesting data sources that live in Hadoop grids, but that is not our only data source. We also have a bunch of stream processing data sources. So at LinkedIn, we're pretty big on Apache Samza, an open source stream processor that we released many years ago. And we have a bunch of Samza jobs that write into Venice. But the Venice architecture is sufficiently flexible that it can support other stream processors as well. We're looking forward to what the open source community wishes to integrate it with, and we'll work with them on that. For this talk, I'm going to use Samza and stream processor kind of interchangeably. We have two flavors of stream processing inputs into Venice. We've got the streaming writes and the stream reprocessing. I'm going to start with the streaming write because that is the one that feels most intuitive and is the most commonly used also. So streaming writes look pretty similar to incremental pushes that we've just seen, right? The main difference is a stream processing job has an infinite input, and so it runs infinitely. Whereas an incremental push has a finite input, so it has a start and an end, like any other batch job. But besides that, the rest is the same, right? The SAMSA job writes into the buffer, gets applied to all dataset versions that exist, and we do support concurrent SAMSA nearline jobs, all writing into the same dataset to union many data sources together. We also support mix and matching, SAMSA streaming writes with incremental pushes, no problem. And coming back to hybrid, a pretty popular combo of data sources that we have at LinkedIn is doing full pushes from a Hadoop grid, let's say on a daily basis or a few times a day, and then also overlaying on top of that some streaming writes. So this is essentially a Lambda architecture that works out of the box, right? Like the user doesn't need to do much. It's all kind of orchestrated thanks to Venice's buffer replay mechanism and all that I described earlier. There is another flavor also of hybrid workload, but where the streaming part and the batch part are actually both implemented as stream processing jobs. This is what we call stream reprocessing. This is possible if the input to your stream processor is an input that supports bootstrapping the entire data set. So Brooklyn is an open source project that does support that we released a little while back. It is our change data capture technology, so you can hook up to, let's say, MySQL or Oracle or other data stores and get all changes that happen in those databases, but you can also bootstrap the entirety of the data set if you want to reprocess all historical data with a new version of your stream processor code. An example of that, a use case, is our Waterloo platform that we have internally, which powers all of our standardization use case. So this is a ML classification use case, like standardizing the people's titles, companies, and many other characteristics. There's more than 100 Venice data sets powered by this that leverage reprocessing. So coming back to our table of write methods, we can now add a new column, which is the stream processing data source or SAMSA data source. And we see that for both techniques, the full data set swap and the insertion of rows, the full matrix of combination is supported, right? There is one more technique for writing into Venice that I want to cover, which I think is maybe the most interesting in a way, which is the partial updates. So partial updates allow the Venice user to declaratively update some columns of some rows of the data set, or alternatively, we have another operation in that framework that we call collection merging, where you can declaratively add or remove items from the collections defined in the schema. So the collections could be sets or maps, and in both cases, the update of columns or the collection merging, you don't need to know what the rest of the stuff in that row is. You just declare what you want to change. So there are a few motivations for having this in Venice. One of them is when you have concurrent nearline writers. I mentioned earlier some of our users like to have multiple data sources get unioned inside Venice. But with partial updates, you can have different data sources, each contributing different columns of the data set. So this becomes now a streaming join, right? And again, you could be performing the streaming join upstream of Venice, like in your stream processing job. But what we found over the years is our users find that operationally intensive, and they prefer to push down that work into the destination data store, like Venice. So this is more convenient for them. But besides convenience, there is an arguably more important aspect, which is correctness. So an alternative design pattern for implementing updates would be to do read modify writes. But unfortunately, if you do read modify writes against Venice, your solution will not achieve correctness. Because you have to remember, all writes into Venice are asynchronous. They all go through this buffer, which means all reads from Venice are potentially stale. And so if you do a stale read, you modify that and write it back into Venice, it's possible that there may be another in-flight operation for the same row that was already in the buffer but that you couldn't read yet. And then your subsequent write will clubber the old one. Essentially, you'll have data loss. And data loss is a pretty big deal. We don't want that. So with partial updates, you don't need to do the read before the write. You just declare what your write is, and Venice takes care of merging it, even in cases where there are concurrent writers. Now, some of you may wonder, well, isn't this like a crutch? Like, why wouldn't Venice just do strong consistency reads and writes like everyone else, right? And I think it's worth opening up a small parenthesis on how is this achieved in other databases. So here, this is not Venice. This is like, think of it as an off-the-shelf traditional database. Typically, the way that they will support read, modify, write workloads is via optimistic locking, right? So the way that it would be implemented is your application does a consistent read, and that read is accompanied with some version metadata of what was that, when was that value written. You'll modify that in the application, and you won't do just a regular write of the modified value, you'll do a versioned write. So you'll include the version metadata that you previously read, and you expect the database to do a compare and swap, right? So the database will compare, is the value I currently have still the one that the user has read earlier? And your expectation is that the database will fail the write if that's not the case. The application then needs to catch those failures and retry the whole sequence. Reread, remodify, and write again. So this pattern, it works. It achieves correctness. But in our view, it is less efficient because, first of all, in steady state, you double the number of operations. You need to read before every write rather than just write. And in case of contention, it's even worse because if you have many concurrent writers for the same row, then all but one of them are going to fail and retry. And this is like not theoretical. We have workloads like this at LinkedIn that are implemented this way, and we do see them suffer in case of contention. So that was sort of a big motivating factor for implementing partial updates the way we did, because partial updates, it's always just one write, no matter how many concurrent writers exist. So it's way more efficient. Now, the final motivation for partial updates is coming back again to hybrid. In some cases, our users want the flexibility of writing different columns from offline data sources versus nearline data sources. So for example, they may have a full push job that runs daily, that writes 100 columns in the table, and maybe they care about 10 of the 100 columns being fresher. Well, they have the flexibility with partial updates to limit the scope of their investment to writing a stream processing job that refreshes just the columns they care about, and it gets naturally overlaid on top of the full push after it comes in. So this is a way to compose these different write methods in very versatile combinations. So putting it all together, we've looked at 3 techniques for writing into Venice: the full dataset swap, the insertion of rows, and the update of rows. And all of these techniques are supported by both offline data sources and streaming data sources. Moreover, what we've seen is you can take any of the full dataset swap method and you can overlay on top of that any of the methods for insertion and updates of rows. So this is a very versatile toolkit for our derived data serving use cases. In terms of scale, the push job runs more than 1,400 times a day, and this is fully automated. There's no human clicking any button, no one verifying that things made it in. It's extremely robust in the way that it checks itself for integrity and end-to-end delivery. It just works, and our users love that it's very hands-off. Out of the 1,800 data sets we've got, there's more than 200 of them that are hybrid, meaning that they're getting either streaming writes or incremental pushes or both. And we see this proportion growing rapidly over the past few years. In terms of the actual volume of the data, if you combine all of the write methods we've looked at, Venice, on average, is ingesting 14 gigabytes per second. That's a big B, not gigabits. And it equates to 39 million rows a second. So that's day in, day out, like continuously, that's what the fleet ingests. But the average is deceiving, as you can imagine, because when you have so many full pushes going on, obviously the write workload is spiky. So at peak, Venice ingests 50 gigabytes per second, more than 3 times as much, and it adds up to 113 million rows a second at peak. On a daily basis, Venice is writing more than a petabyte of data and more than 3 trillion rows. So this is one of the data systems at LinkedIn, I would say, that ingest the most data. Now that we've talked about all the various ways that you can write into Venice, let's talk about getting data out. So in this section, I'm going to go over several use cases to kind of give you a glimpse of the versatility that these APIs afford us. So the simplest way to get data out is to treat it as if it were a key value store. Just get the value of a key. Adding up all the data sets, we've got more than 6 million queries at peak that are leveraging this API. And one of the prominent example of this is T-Rex, our A/B testing platform. So this is an example of a non-AI use case that benefits from these abstractions that I presented. They ingest a bunch of data from Hadoop and from streams, which are essentially member attributes data, like their geography or their industry or stuff like that, which are characteristics that our A/B testing platform supports for targeting more specifically the tests, right? And at LinkedIn, we're super big on A/B testing. At any given time, we have thousands of A/B tests going on. For a single request to the site, like just a page load, you could be evaluating hundreds of different A/B tests for all the various functionalities that we're ramping, or even just major code changes that we're ramping. So this is basically a way that Venice gets indirectly used by pretty much the whole company. Another way is batch get, where you want to get the values for a set of keys. This is very popular for AI use cases in the search and recommendation space. And for those, we tend to prefer not measuring the workload in terms of queries per second. We have found it more useful to look at it in terms of key lookups per second for our capacity planning and stuff like that. All in all, with all data sets, it adds up to 45 million key lookups per second that are leveraging this API. One of the big examples of this is the feed. So when you go in the app and you got like a feed of posts, basically the way this works is it's a recommendation use case that will evaluate out of, let's say, several hundred candidate posts that it might show you. For each of them, it's going to query a bunch of Venice stores where it fetches a bunch of machine learning features that belong to each of those posts. Then it's going to run ML models to infer a score for how relevant each of these posts is for you personally. And it will return the top K most relevant posts, right? So this is a very high throughput usage of Venice for the feed. The third API and final read API that I want to present is read compute. And this is potentially the most exciting. This is a declarative DSL that allows you to specify certain operations to execute on the server side in Venice. And so the server will look up the keys you ask it to, execute these operations, and return only the results back. With this, we can project only some of the columns if you're not interested in the whole row. And most importantly, we also support some vector math operations, which are very useful for AI models. So things like dot product, cosine similarity, these are mathematical functions that have as input a pair of vector of floats, essentially, and the output is just one scalar, one float. So the input is way larger than the output, and so it makes a lot of sense for us to do that co-located with the data in the server so that the response sizes that we ship back to the clients are much smaller. The read compute use cases add up to even more kilocups per second than the batch gets, 48 million kilocups per second at peak. And on average, each of these keys getting looked up is performing roughly 10 vector math computations. So that's quite a lot of computation that's happening inside the Venice servers. An example of this is people you may know. They are leveraging Venice Read Compute to do online deep learning at scale. And we think this is fairly significant because although nowadays deep learning at scale has become more common, we typically see that happening offline. Like in a Hadoop grid, you'll be trashing out the whole grid to do your deep learning. That's fine. But when you transfer that to the online context, like answering a request from a user, typically, the way that we've seen people implement that is that they'll have, like, let's say, a TensorFlow model or PyTorch or whatever, and they'll distribute that to their online apps. But a given request is getting served by just one application instance, which means that your entire model needs to fit in that one box. And typically, you want it to fit in RAM. So it's sort of not very permissive of having large models. In the case of PYMK, it doesn't work for them because they have multiple terabytes of feature data that they want to reference. And so with this solution, we're allowing them to scale on commodity hardware because they can fan out their queries to a bunch of partitions of the Venice servers and have essentially the model be evaluated in parallel across all these servers. So far, we've looked at single get, batch get, and read compute. And all of that was in the context of what we call classical Venice. Since 2020, we also have an alternative client library for Venice that makes a very different cost-performance trade-off. We call it DaVinci. So DaVinci is essentially a portion of the Venice server code packaged as a client library. It means essentially you're running like a mini Venice server inside your application. It exposes the same read APIs as classical Venice, so get, batch, get, compute, plus some APIs to subscribe to some partitions or all partitions of the data. When a partition is subscribed, it means that queries will be served from the local state inside your application, either RAM or SSD, depending how you configure it and of course, what you have available. DaVinci is what we call a eager cache. In opposition to a read-through cache. And I want to spend a little bit of time disambiguating what are the differences between these, because eager caches are probably not familiar for most people. The eager cache loads everything up front and keeps listening to further updates, which is different from a read-through cache that organically populates itself according to the traffic it needs to serve. With the eager cache, importantly, there is no time to live. There is no TTL that you need to configure. So here, I'm showing these two side by side, and I'm breaking up the read-through cache into essentially two separate solutions, right? If you configure your read-through cache with high TTL, you'll benefit from a higher hit rate in the cache. But since you'll be hanging on to stuff for longer, the stuff you're serving out of it is more stale. If you care about freshness, you'll want to lower your TTL. But then that will degrade your hit rate. So you've got this awkward trade-off that pits hit rate versus freshness. With the eager cache, it is superior to both, actually, on both dimensions. The hit rate is always 100% because you've got all the data locally. And it is also maximally fresh because you're actively listening on the change log. As soon as something changes, you're already refreshing yourself. With a read-through cache, you get cache misses, of course. And that means you pay the cost of the latency of a remote query. With the eager cache, it just never happens. So if we look at these dimensions here, we see that the eager cache is strictly superior to the read-through cache. But of course, you know as well as I do that in this world there is no free lunch. So what's the trade-off, right? The trade-off essentially is in the size of the local state that is required for these solutions. With the read-through cache, you have the nice property of being able to configure the maximum size of the cache, and it will evict whatever is sort of doesn't fit based on least recently used or some other fancier algorithm. Typically, you will set this to a much smaller size than your total data set if you're, because typically the hot portion of the data set is kind of a small fraction, which means that for a relatively small cost, you get a performance boost on some of your data accesses, which is a great deal in many cases. With the eager cache, on the other hand, you must have enough provisioned resources on your application to hold the entirety of all the partitions you subscribe to, which may be all the partitions if that's what you want to do. Finally, this last dimension of comparison is the bandwidth requirement of each solution. And on this one, it will sort of depend on the workload which one comes out on top, right? For the read-through cache, you need enough bandwidth to support all of your cache misses, so it's proportional to that. Whereas with the eager cache, you need enough bandwidth to ingest all the updates to the data set. And again, depending on the workload, it will depend which one is sort of more costly. I'm going to quickly run over 3 different use cases of DaVinci to kind of give you a glimpse of the scope that it can support. The first one is the simplest. We have some ads applications, which are basically just bread and butter, simple online applications that would otherwise be stateless, that need to query some Venice data, but they want to do it really fast, and they can't afford to do the remote call to the backend. So they use DaVinci, and it works great for them because their total data set is pretty small, like less than 10 gigs. So they can afford to have everything loaded in each of the app instances, and they have many replicas, of course, of the app instance. They put everything in RAM because they want things to be fast, because there's money to be made. So another use case, which is a bit more sophisticated, is Galeem. That's our proprietary search infrastructure. And in that case, the data set size that they want to have is bigger, 100 gigs, maybe 200 gigs. And so they need to partition it because they don't want to have like 100 gigs of like ML features on each of their searchers. That's sort of a bit bigger than comfortable. So they will typically partition in like, let's say 16 partitions or maybe 32 partitions, basically a small number of partitions. And each of their searcher instances will subscribe to just one of them. But because their workload is pretty expensive, they do their read scaling by having lots of replicas. So they will have sometimes up to 60 replicas. If you add 16 partition times 60, that comes up to a search cluster that's maybe 1,000 nodes that are all subscribing to the same Venice data set by leveraging DaVinci. And they put all that in RAM, because again, they're very latency sensitive. The third use case is SAMSA. Now, I already talked about SAMSA earlier as a data source for putting data into Venice, but we also have a bunch of SAMSA jobs that read a ton from Venice. Some of them are so intensive that they just sort of can't keep up if they need to pay the hit of a remote query on every event they process. So they will do local state instead via DaVinci. And in this case, we have a team that has a couple of use cases here that are in the tens of terabytes of state in total, so quite large. And so what they will do is they will partition in a much more fine-grained way. So they will do 1,000 partitions, sometimes 2,000 partitions, and each instance will have just a few of them, maybe 1, 2, or 4 partitions in each stream processing container. For stream processing, typically you don't need a lot of replicas. 1 is fine, maybe 2 if you want a warm standby. So again, this is a use case that has, let's say, 1,000 containers doing stream processing. All of them are subscribing to a Venice data set. And in this case, they shove it in SSDs because it's more cost effective for them this way. So looking at Gallina and SAMSA, the takeaway here basically is Venice is not just a standalone system that you can query. With Da Vinci in the ecosystem, it now becomes a building block for other distributed systems. And you can see the versatility of like, low partition count, high replication factor, or the opposite, RAM, SSD. You can use it sort of in many different ways. So now, I want to sort of move away from the user-facing aspect and talk more about what it's like for operators to run Venice. Venice runs at LinkedIn, which has been operating with multiple data centers for a while. Since we started the project, we were already in multiple data centers. So it's always been a hard requirement for us to do cross-data center replication. For many years, we were doing active-passive replication, which means you could have data coming of a Hadoop grid in just one of the data centers, and that would go everywhere. But starting about 1 or 2 years ago, we ramped up efforts to rewrite this replication implementation, and now Venice is active-active. So that means you can push from any grid from any data center. And likewise, for our stream processing cases, you can have SAMSA jobs that exist in all data centers that are all writing concurrently and get replicated everywhere. These are important characteristics for both our operators and our users who want the data in Venice to remain fresh, regardless of whether some data sources in some data centers may be unhealthy. In that case, the sort of redundant data sources in other data centers kind of pick up the slack. Now, if we zoom into one of these regions, we see that each data center has a bunch of Venice clusters in it. Currently, we have 17 clusters per data center. And what's nice about this is that the assignment of a data set to cluster is completely operator-driven. So the operator sets some policies where at onboarding time, the use cases will go here or there. And then they can, if they want, manually override that and change it. And they can migrate migrate data sets across clusters. And all of that is completely invisible to users. The user only configures what their data set name is. When writing to Venice, when reading from Venice, they never know what cluster they're in. Well, unless we tell them, but they don't need to know, right? Now, let's keep zooming in. In one of these clusters, we have some clusters that are dedicated to our power users, like the ones I mentioned, the A/B testing platform, the feed, people you may know. These are some of our power users that have dedicated clusters. But we have roughly half of the clusters that are multi-tenant. Some of them very heavily multi-tenant. Our busiest cluster has more than 500 data sets in it. And you can imagine that there's a lot of noisy neighbor issue, potentially, right, in such a highly densely populated situation. So what we do is we have quotas in place for both the storage space that a data set is allowed to use and the read throughput that they can query. And if they go over that, they get capped, and it allows us to ensure that the other tenants in the cluster can keep running smoothly while the tenant that went overboard figures out, is that a bug in the application, or they poorly plan their ramp of their next functionality or whatever. And of course, they can ask for more if they need. Also, within the scope of a single cluster, we care a lot about scalability of each individual clusters, right? So we leverage Apache Helix to do the partition and replica placement of the data inside the clusters. And this is very convenient because we can throw in fresh hardware into a cluster, and it will automatically rebalance the data. And because Venice is so optimized at high volumes of ingestion, this leverages the exact same code path, so rebalancing is also fairly fast. Now, another aspect of scalability is that as you add hardware, you want your capacity to increase linearly in proportion to the amount of hardware you added. And for the read traffic heavy use cases like the feed and PYMK, what we need to do to sort of serve them is add more replicas of the data because they're just doing so many queries. So we achieve linear scalability in that scenario by grouping the partitions into replica sets. And that means that even though, let's say, the feed is doing a batch get that will need to touch all partitions because they're asking for hundreds or thousands of keys, we limit the blast radius to some bounded number of servers. And that allows us to keep scaling linearly. We have a blog post on this particular subject if you're interested to learn more. In conclusion, we've seen that Venice is optimized for ingesting rapidly changing data, no matter if it comes from offline or streaming or composing any combination of these. We use it quite a bit for feeding our online inference workloads, but it can also be used for non-AI workloads, an example of which was the A/B testing platform, which is widely used at LinkedIn. We are open sourcing this today. I'm about to click the button to make the GitHub public. So let's see. Let's see if that's going to work. OK. Do you see this? I didn't try it before, but I was told it will work if I have internet. OK, great. So I think I need to come down here. Oh, yeah. Geez. OK, this is exactly the type of stuff I should have checked, that the two-factor auth would not need to be refreshed. // OK, I guess we'll have to do this thing now. OK. Anyway, as I'm doing this, thanks a lot for listening, and we really look forward to seeing what the community does with this project. We have several aspects of the system that we think are extensible, like adding new stream processors and other aspects. And by the way, I wanted to say also that I've discussed basically just what I consider the rock solid parts of Venice, right? The things that have been running in production. We have a roadmap packed of experimental things we're working on that we're looking to make more robust over time and publish more information about. And finally, it is time to close issue number 1. Okay. All right. Thank you.